Hello. This is the first chapter in a series of new videos where we walk through the organic chemistry textbook through Top Hat. We're switching to this year, and so I wanted to go ahead and make some new videos. So I'm using the textbook as a guide, something like that, and so I'm not going to use a lot of the material from there. I'm going to be using it from the material from previous textbooks. Stuff like that, but the material itself is going to be the same, something like that. So the slides may look different than what you see, or the figures, or whatever, what you see in the textbook, but the material is basically the same. So, so to start off with, what we really want to talk about is what is organic chemistry. Organic chemistry is the chemistry of carbon atoms, but that carbon it's called organic because it's the basis of life. We are based on carbon, but that carbon has some very unique properties to it compared to any of the other elements in there, in that it can readily make single, double, and triple bonds. It can and it's incredibly flexible in what it can do, unlike a lot of the other atoms. And so, not only is it the basis for life, but it's also the basis for a lot of the products that we use in our day-to-day lives, something like that. And so the most obvious one are going to be the pharmaceuticals. Something like that. There's still, small molecule ones are still incredibly important for medicine. And even the biological ones, those are just mostly probably proteins, things like that, which are organic based. And a lot of the polymers that we use. So with the plastics, polymers, whatnot, those are all going to be, nearly all of them are going to be organic based. But also other things like fabrics, whether they be cotton or synthetics, like polyester. Those are all organic molecules, along with the dyes that color them. With that, so most of those are going to be organic dyes. But, since we're dealing with biological systems, it's also, if you're looking at nutrition, a lot of the vitamins are going to be organic based. So for that, so in this case, this is riboflavin. The reasons why it's called riboflavin is this part down here of the molecule is composed of is derived from a ribose molecule, and then this part up here is generally called a flavin, and so it's a ribose attached to a flavin, so it's called riboflavin. Okay, and so we're going to be the basics for this. Organic chemistry is making and breaking bonds to carbon, and so the first part of this chapter is going to be about the figuring out why things like to make bonds. Okay, and so we're going to start in here. We're going to deal with deal a little bit with quantum mechanics and dealing with orbitals and things like that. This is just supposed to be a review for general chemistry. That's what a lot of this this chapter is, and it's just to set you up, to remind you how to, what things are going to be important down the road for when we're talking about organic molecules. So quantum mechanics, we are not going to do a deep dive into this. If you want to, you can take a physical chemistry course at your local school. If you're a chemistry major, you're probably going to have to take it. But do realize that it's the one branch of science where the more you know about it, the less it makes sense. Something like that. So somebody described it that way, and I thought that was perfect. But anyway, we are going to touch on it a little bit. Okay, so the first thing you have to realize with quantum mechanics is that most of the time we're going to be dealing with, when we deal with positives and negatives, we're going to be dealing with mathematical signs, not positive charge, negative charge. Okay, and so if you see a negative, most likely it's going to be a negative number as opposed to a negative charge. So we're going to be dealing a lot with this constructive and destructive interference. And so if you have two waves and they've got values throughout the at different points for that. So if you have two waves and you want to add them together, if you get constructive interference, the values, when you add them up, so that get something larger, right? So if you have +4 or +4 and +4, right, they're going to be +8. Same thing if you had -4, -4, right? They would be -8. and it would go, and that's how you get constructive interference. If you have destructive, right, you're trying to add up numbers that it would be like +4 and -4, and they're going to, the number's going to be smaller. And so in this case, it would be 0, right? No matter, because they're equal and opposite, when you add them up, it's always going to be at 0. Okay, so we're going to be using this a lot to explain what's going on with atoms. Okay, so how we're going to be using a lot of these things we're going to be dealing with are the electrons, and so how are they going to be distributed around the atoms? And so with the atomic, most of the time they're going to be arranged in atomic orbitals, and there's really 4 different types, but 99% of the time we're going to be dealing with the s and the p orbitals. The s are sort of are spherical shape, and since there's only one type, you can only have one pair, and each type can have 2 electrons. For the p orbitals, are sort of dumbbell shaped, and there's 3 different kinds of it. Each one of them can have a pair, and so you can have a total of 6. D orbitals, right? See, there's 5 different types. They kind of, it's cloverleaf, and there's some other ones too. And so for that, you can have 5 pairs of electrons, or 10. And with the f orbitals, there's 7 different types. Each one of those can have a pair of electrons, so 7 pairs or 14. And notice how it goes 1, 3, 5, 7. They're an odd number of types of orbitals. Just a little quirk. Okay, so we're going to be filling these things, but again, nature's lazy. It would much rather be out sitting on the couch than going out into the gym and working out. And so it's going to start filling the electrons into the lowest energy orbital. And in this case, it's going to be, you can generally look at the shell numbers, so 1s, 2s, 3s. Generally look at that, and it's going to fill the 1s before it fills up the 2s, which is going to fill up before the 3s. Okay. And so with the s orbital, remember, with the s orbital, it's spherical. With the p orbital, remember, there's 3 different types, and it's it's where these lobes are positioned. If they're along the x-axis, we call that the px. If it's along the y-axis, we call it the py. And if it's along the z-axis, which is coming out, normally coming out at you, we call it the bz. And so you're going to have 2 different lobes, one that's going to have a positive value, one that's going to have a negative. Remember, these are mathematical. And the space in between there where there's no electron density, that's the node. And so you can look at this, and like that. Okay. So how are we going to configure these things? So there's a couple of different scientists contributed to this one. The first one is Aufbau. What he said is like, okay, you're going to fill this up in the lowest energy orbital. So how do you figure out how you're going to fill these things up? Well, you can memorize these things, or you can just look at the periodic table. And it turns out if you go across, it'll tell you which orbital you're going to have to fill up next. Okay, so the 1s is weird because of the positioning of hydrogen and helium, and the fact that it only needs 2. After that one is the 2s, right? So this is going to be the s block, d block, p block, and f block. And so as you come across, the next one you want to fill is the 2p. Now the first orbital type you came to was the s type, so you start with 1. The next type of orbital you come to is the p type, and so since the second one, it starts at 2. At least that's how I always remember it. Come over here, 3s, right, because you already have a 1 and a 2, 3s. Come over here, you already have a 2, so let's start at 3. So you come across here, over here, the 4s, and then this one, you come to the f block. Now this is the third type you've come to, and so this one we're going to start off with D, with 3D. And I always remember this because, remember the 3D movies that were so popular a while back. So that's how I remember it, that you're going to start off with 3D. So you're going to start filling up the 3D orbital, and then start filling up the 4p, and then come back here, 5s, 4d, right, because you already have a 3d, and then 5p, and so on and so forth. So that's how you're going to fill it. So you almost always have a periodic table on tests. So so that's what I think the easiest way to look at it. Okay. Pauli come in and said, okay, so you can have 2 electrons per orbital, but they have to be different. Otherwise, they have the same quantum numbers. And so he said, okay, so the difference, if you have 2 electrons in the same orbital, the difference between them is that their spin is going to be slightly different. One's going to be, we normally say one's going to be up, one's going to be down. So they have to have opposite spins. Okay? Hunt came in and said, okay, yeah, they don't mind being paired up, but what they would really like to be is they like the fairly antisocial. If you've got the option of having them unpaired, that's better than having them paired up, and until you get to the point of the everything filled. Okay, so like for this one, so if you look at carbon, you have two electrons in its p orbital. Okay, instead of having both of the electrons here and then two empty orbitals, what it says, what Hun says, like, look, you're going to have one electron here, one electron there. For that, and it kind of makes sense because you have two electrons. They're both going to have negative charges, and so they're going to repulse. And so we'd rather keep those negative charges apart if possible, right? If we have to pair them up, fine, but we want to wait as long as we can. Okay? And so if you look at the electron configuration of sulfur, so sulfur has 16 electrons on it total. Okay, and so you're going to start walking across the periodic table. So you come to 1s, and then come back over 2p or 2s, and then 2p, and then come back over here 3s, and then you have 4 electrons left, right? Because you've already used up what, 12? So you got 4 left, and so you would go like up, 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 and then whoop, we got another one. So one of these is going to have to be a down. We're going to have to pair it up to be a down. Okay? And so this lets you know, gives you an idea for how these electrons are paired up. Okay, and so there's two different types of electrons we're talking about. The core electrons are where everything in that shell is completely filled. Everything's paired up. We're good to go. It's going to have the same electron configuration as one of the noble gases. The highest shelled electrons, though, those are the valence ones. Those are the ones that are trying desperately to get completely filled up. Okay, and so sulfur, it's going to have so 1, 2, 3, 4, 5, 6. Okay, and so if we do this, right, so it's going to have 1, 2, 3, 4, 5, 6 electrons around it. And if you notice, this also goes with oxygen. It needs 2 more electrons. If it gets those, then it'll have a octet. And so what it's going to want to do is make a bond here and a bond here, because remember, a bond is 2 electrons. A covalent bond is 2 electrons. And so if it pairs up, one here and one here, if it shares it, it can make it can fill up its octet. Okay, and so this is why sulfur and oxygen and whatnot want to have 2 electrons and 2 bonds. If you had nitrogen, you wouldn't have this one here, right? What does nitrogen want? It wants a lone pair and 3 bonds. If you have let's say the fluorine atom or any of the halides, you're going to have one here, so it's going to have 3 electrons and 1 bond, so it can get its octet. So the reason why we go through these things is it sort of helps you sort of predict how many electrons it wants, how many lone pairs and whatnot. Okay, so atomic orbitals are great, but the problem is once you start pairing these things up in order to make bonds, the atomic orbitals can't handle that, and so the math breaks down. So if you just have a lone hydrogen atom, it's fine. If you have a lone carbon atom, that's fine. Once you start making bonds together, that math breaks up. And so what they have to do is they have to combine these atomic orbitals into molecular orbitals. Okay, and so the linear combinations of atomic orbitals. Okay, and so again, we're going to be talking about math. And so if we have 2 atomic orbitals, okay, so in here these are hydrogens, so it's we have an electron in this orbital and then an electron in this orbital. We have a plus and a plus, mathematical plus plus. If you add them together, right, they build up, right? So you're going to have a lot of extra electron density here. You get constructive interference. If you have a plus 1 and a minus 1 mathematical, right, you're going to get a node here, something like that, because they're going to mathematically cancel each other out. So there's not going to be this. When you have constructive interference, we call that a bonding molecular orbital. If you have this destructive interference, it's called an antibonding. And now, because you're combining 2 two s orbitals, it's the type of bond that's made is called a sigma bond, because the the Greek letter s is sigma. So since you're combining two s orbitals, it's going to be a sigma bond. Now so the one where you have the node, you have deconstructive. We typically talk about this as a sigma star, or it's anti-bonding, because they're literally not wanting to bond those two electrons together. Okay, and so if you have two orbitals where they interact, you get constructive interference so that the atoms can stick together, they're going to bond together. That's called a bonding molecular orbital. If when you put them together, you have destructive interactions with that, and that's what's called antibonding, and so that actually has a higher energy. Luckily, the bonding has lower energy, right? So it wants to be bonding. You can also have non-bonding molecular orbitals, and that's where they don't really change. This is where we're going to stick lone pairs, stuff like that, eventually. Okay, and so there is a conservation of the number of orbitals. So if you have two atomic orbitals, you're going to get two molecular orbitals out. Half of them are going to be, well, in this case, one of them is going to be bonding, the other one's going to be anti-bonding. Okay, so you get two in, you're going to get two out. Okay, and the highest occupied molecular orbital is going to be this one down here. So that's that's the HOMO, and then the LUMO is the lowest unoccupied molecular orbital, and so that would, in this case, it would be this. Okay, it's just, and so you can use that, whatever that the gap is here, to predict if a reaction is going to occur. That's a lot of physical organic chemistry. We are not going to get into that, but do you know that these things exist? If you look at HOMO-LUMO gaps, things like that, you can make some predictions on whether a reaction is going to occur, and some other things. But again, if you have a sigma bond, okay, so remember the Greek S is sigma, it's a bond between two s orbitals. Okay, so, but the thing is, how do we account for bond angles? Okay, so if you try to do this for particularly for carbon, the bond angles are wrong. Okay, and so what happens is, it turns out, in order to be able to take that into account, you actually have to hybridize it. So mix the s and the p orbitals together, and this becomes incredibly important for carbon. Okay, because if we take an s orbital, okay, and we take a p orbital, and we combine them mathematically, what we get is this side is going to be constructive, this side is going to be destructive, and so you're going to get a big lobe over here and then a little lobe over here, so it's going to look like this. Okay? Same as if we were to flip these things, you could have the other one, and so you're going to have the and so you would end up with this hybridized thing. And so if you have one s, and one s and one p, you have an sp hybridized orbital, because you combine one of the s's and one of the p's. Okay, and the orbitals themselves, remember, you're going to get you're putting two orbitals in, right? So you better get two out. Okay, so you're going to get one going this way, one going this way, right? One going this way, and they're on the same atom, and so they're going to be 180 degrees apart. If you combine one of the s's, oh, and remember so remember that you have the p, the y, and the z, the py, the px, the py, and the pz. In a hybrid orbital, the other two that are not hybridized, right? So if we're going to come in here and we're going to hybridize the px and the s orbital, okay, the py and the pz remain unchanged. Okay, so we haven't dealt with them; they're still the same shape. It's just this sp orbital that's changed. Okay, and it's whether you do the x, the y, or the z, it doesn't matter. The other two are unchanged. Okay. Now if we combine two two p orbitals and an s, okay, we get an sp2, right? An s and two p's. In this case, again, we're going to get one atomic orbital, two atomic orbitals. We're going to get three total, so we're going to get three lobes, right? So s, p, and p. The other one that we have not combined does not change. Okay. So with that, but if you do the math, the way you separate out the most is if they're 180 degrees apart. So 3 orbitals in, 3 lobes out. Okay? And if we combine one s orbital with all 3 of the p orbitals, now we get an s and a sp3, so spp, sp3. So that now the orbitals are 109.5 apart, and so like these guys here, the green and the yellow are going to be in the plane. This red one is coming out at you, and the blue one's going behind to make a tetrahedron. So we're putting 4 orbitals in, so we better get 4 lobes out, right? 1, 2, 3, 4. And it turns out that that's a tetrahedron shape with 109.5. Okay? And so these are what the orbitals look like. So this is an sp, sp2, sp3, right? sp, so you're going to have 2 lobes. sp2, spp, you're going to have 3 lobes out, 1, 2, 3, right? For the sp3, right, sppp, you're going to have, you put in 4 orbitals, you're going to get 1, 2, 3, 4 lobes out. Now the bond angles are good to generally remember. That these things can change a little bit as needed, but it's pretty good to remember, okay, in general. Okay, so what about molecules though, beyond H2? Okay, and so again, we're going to be dealing with this valence bond theory, where you have this core electrons that don't matter, right? So once you fill up that 1s, right, you put 2 electrons in there, they don't care anymore. Okay, now you're going to have to deal with the outer shell of electrons. Okay, so the s and the p orbitals in that highest shell, and it's those that want to combine so that they can make new, they can get the atoms its octet. Okay, and so what you're looking at, what you get is if you have a carbon and it's sp3 hybridized, so it's taken its s and all 3 of its p's and hybridized them, these sp orbitals can actually overlap with an s orbital. Okay, it can also overlap very nicely with the with another hybrid orbital. Okay, so you get a nice overlap here and a nice overlap here. So that allows, so if you have 1 electron in this orbital and 1 electron in that orbital, right, you're going to make a nice bond. Same thing in here, right? Hydrogen has 1 electron. Carbon's going to put 1 electron in this hybrid orbital, and you're going to make a nice bond there. They can share it, and hydrogen has its 2 electrons. The carbon has its 2 electrons from this, and everybody's happy. Okay, and so a sigma bond, we're going to expand that a little bit. You can either get it between, because it has very similar properties, from 2 s orbitals, a hybrid and an s orbital, or between 2 hybrid orbitals. So this is a sigma bond, and that's a sigma bond. Okay, but that, and because you're making them, right? So with that, so you have a sigma bond is the you make a single bond, but you can also make the equal number of antibonding. Okay, sigma bonds turns out are going to be the most stable. Okay, and so with that, and so they are the lowest energy. Conversely, the sigma antibonding, so the sigma star, because these are the lowest, right? There's a conservation of energy. If these are the lowest, then these have to be the highest. These 7 antibonding has to be the highest. Okay. So you guys can see this. Oop. Okay, so, but we know from the, if you remember back from general chemistry, we had to deal with doublets and triple bonds. Now there are quadruple bonds. We don't have to deal with that because those are typically between metals. So we're just going to be mostly dealing with non-metals in this course. Stuff like that. But they can still make double bonds. Okay, they also make triple bonds. We'll get to in a second. So if this is a right, so this is 1 bond. If we want to put another set of electrons between that, what we're going to actually have to do, remember, so these hybrid orbitals are facing away from the other atom, right? So these guys are pointed out that way, right? These lobes are pointing out that way. So what's an atom to do? Well, what it does is it says, okay, let's use these 2, this unhybridized orbital here with an electron in it, and this orbital here on this unhybridized p orbital, and what we end up getting is if you extend this out, you can get overlap here, especially in here. You can get overlap here and here, and that allows you to have a bond. Okay, and so if these things overlap constructively, you get, you know, overlap here and overlap here. So overlap positive math, negative math. But you can also have an antibonding where they're head to tail, and so again you're going to get deconstructive. Now this, and so because we're combining two p orbitals, right? The Greek letter for p is pi. We call this a pi bond because you're dealing with two p orbitals, and so this would be a pi bond, and this would be an anti-pi bond. Okay, and so pi bonds aren't nearly as stable as sigma bonds, and so they're not as, so you don't get quite the bang for the buck here. But then that also means that the antibonding isn't quite as unstable. Okay, because remember, there's a conservation. If we're going to move down this way, right, we got to move up this much. But the sigma or the sigmas and the sigma and sigma star are way out here, but the p orbitals, you don't get as much down, but then you also don't get as much up. Destabilization. Okay. And the reason for this is the fact that there's not as much overlap. Okay, this is not right. These two are kind of pointed up like this, and these two are pointed up like this, and so they're kind of sidling up next to each other, and so they have to get closer in than they normally would when you've got this orbital here and this orbital here. They're designed, you know, well, I won't say designed, but they are right where they need to be, pointed right at each other, head to head. There you go. Now we can also have antibonding. Okay, and so you've got this these two hybrid orbitals to make the sigma bond. You've got right. You've got this here and this here. You need both parts to make a pi bond. Okay, so that's the second one here. But then what do we do with these guys here? Okay, let me get a different color. So what do we do about these here? Those electrons. So where are we going to put those? Well, those are the antibonding. That's here and here. They're antibonding because there's nothing there, right? It's not bonding to anything, and so it's considered an antibond or a non-bonding orbital because it's not bonding to anything. So this is where we're going to put our lone pair. Okay. Okay, now with triple bonds, it's going to be similar to the double bond, except now you've got a second set of p orbitals. Okay, so you have the so if you only have sp hybrid, right, the other two orbitals on that atom are going to be unhybridized, and so the green ones are going to, or excuse me, the blue ones are going to be sort of in the plane like this. They're going to overlap, and then the green ones are going to be coming out at you. Okay, so with that, so they're coming along the z-axis here, and so this one is going to interact with this one. This one is going to interact with that one. You're going to make a second pi bond. Okay, and so you get a sigma pi on here, but it works the same as if you're dealing with a single double bond. And again, you're going to have the pi molecular orbitals here and here. So this one would be, so like this one would be there, and this one would be there, right? And again, this one would be there, that one would be there. Okay, so if we want to count the sigma and the pi bonds, right? So we're going to get to what this drawing means in a minute. So carbon, 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 carbon. Okay, and so for here, right, there's only one bond. So you're always going to have a sigma bond, right? Because that's the most stable. So it wants to make a sigma bond first, but there's no additional bonds between these atoms, and so there's no pi bonds. For this one, between this carbon and oxygen bond, right? We always have a sigma, but the second bond is always going to be a pi bond, and so we have one sigma, one pi. And for this one here, between these two carbon atoms, right, the first one laid down is always going to be sigma. So you're always going to have a sigma no matter what, because it's the most stable. And then the other two have to be pi. And so this one, so then you've got 2 pi bonds. Okay. And these are the only ones that we're going to have to deal with in this course. Okay, so dealing with hybridization, okay, so what you're going to need to do, and I'm going to, dang it, it's always forget about this. So for the, I need to move this up. What's going to happen is we're going to see we're going to have to figure out how many letters that the atom needs, okay? And so for there, we count the sets of lone pairs, okay, and then the bond sets, okay, and that's going to tell us how many letters we need. And the first one's going to be S, and then just like we're always going to have an S, a sigma bond, and then multiple pi's. Same thing here. We're going to have an S, and then we're going to add p's, stuff like that. But remember with the set, a single, a double, and a triple bond each count as 1, okay. And so if you're looking at that carbon there, okay, it doesn't have any lone pairs on it, but it has 4 bond sets, right? 1, 2, 3, 4. Okay, so it has 4 single bonds. Okay, so it means you're going to have 4 letters, and so you're going to go S, P, 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 sp3. With that, so with this one here, again, there's not going to be any lone pairs, but you've got the single bond, this single bond, and that double bond, right? So those are 3 sets. 1, 2, 3. So in this case, you need 3 letters: SPP, SP3, or excuse me, SP2. Stuff like that. So it's SP2 because you've got 3 letters at SPP. Okay. And then for this oxygen, right? You've got two sets of lone pairs, right? Right here and right here. And then you've got 2 bond sets. So one there and one there. And so you're going to need 4 letters, and so SPPP. So SPPP or SP3. And so you can write it as SPPP, right? If it's easier to think about, an SPPP, right? Or you can write it as SP3. So it's just whatever you're comfortable with. Okay, so if you want to determine the hybridization on this thing, so for this carbon, right, it doesn't have any lone pairs, right, but it does have 2 bond sets, this one and this one. So 2, so we need 2 letters, so it needs to be S and P. For this one, again, we're going to have no lone pairs, but you're going to have 1, 2, 3 bond sets. So we need 3 letters, so SPP or SP2. And then for this oxygen, right, we have 2 lone pairs, right, here and here. But then we also have, right, this bond set there, so 1, so we need 3 letters, so SPP or SP2. So there you go. Okay, now one of the things that happens with this is that you are going to get rotation. So if you have a sigma bond and only a sigma bond, notice how there's nothing holding it steady, and so they're actually you're going to get free rotation around that sigma bond. Okay, so if you have a single bond, you're going to get rotation. If you have a double or a triple bond, you're not going to get rotation. And the reason for that is, remember, the orbitals, the p orbitals, have to be aligned. And so if you're going to try to get rotation on this bond, you're literally going to have to break the p orbital overlap. And so these things are fixed, and so those have implications down the road. Okay, and so for here, these carbons here aren't going to be like rotating around like this. Neither is this hydrogen and carbon. They're not going to be. They're going to be fixed. Now everything else is going to be rotating around, but not these atoms here in the orange. Okay. And so those are going to be fixed rigidly. And because of that, we can have what's called cis and trans isomerization. And so you need to have, so you can tell if it's cis or trans if you look at the, so in order to do this, you have to have one hydrogen on one side, one on the other. So you'll hear us talk about substitution down the road, and the easiest molecule to deal with is ethylene, something like this. And if you have just a straight hydrocarbon, when you say you're substituting, what you're doing is you're saying I'm substituting what would normally be a regular hydrogen for something else. And so for this one, right, we're substituting, these two hydrogens for chlorine atoms, and then for here, a chlorine atom for here and here. Those are the substitutions. So so that's what you mean. But for here, right? Notice how. But the other way you can do this is say, okay, if you're talking about cis and trans, where are the hydrogens pointing? Because you have to have one on each side. Which way are they going to be pointing? And so for here, right, the hydrogens are pointed both down. So if they're both pointed either both up or both down, it's going to be cis. Trans, right, the opposite, right? So one up, one down. And so for here, notice how the hydrogens are both pointing down. So this is the cis, and this one here, one up, one down, that's going to be trans. And so they do have, even though they're the same molecule, right? They have different boiling points, right? The only difference is how the atoms are arranged. So these two isomers are going to be a little bit different. Now, we see this in biology. Again, if we talk about saturated, that means we've put in as many hydrogens as possible into the molecule. And if you're saying unsaturated, meaning we don't. So for that, and so most oils, okay, are going to be unsaturated, either unsaturated, and if they do, they have a cis double bond. Notice how, again, these hydrogens are pointed in the same direction. Or it's going to be saturated, where it's just you don't have any double bonds in them. Okay, so when you want to make, say, Crisco or margarine or whatever, what you're going to do is you're actually going to add hydrogens to this to turn this double bond into new CH bonds, and it goes like this. And so and the reason why this is an oil and then this is usually solid is, imagine that you're on a platform for a subway or a train or something like that, and it's busy, it's rush hour, and so everybody's standing pretty straight up. Okay, so people can really pack in there. So but that's this situation here. Notice how it's straight. If you have a cis double bond, what happens is, and you can't see this, you get a kink. Now imagine what would happen if that kink if everybody was bent over. You couldn't pack as many molecules in there. It's a little more complicated than this, but it doesn't pack as efficiency, so it's not the and so it's going to be a liquid. There's not as much interactions between the molecules, and so it's going to be a liquid. Now you hear a lot about trans fats, and what's happened is when you're converting saturated to unsaturated, okay, sometimes the reaction can go backwards, okay, and when it does, it turns out that the trans is more stable than the cis, and so it forms a little bit of the trans fat. And again, you can see this with hydrogen up, hydrogen down. Most of biology is going to be this, is going to be the cis, and so we have enzymes that we know how to break. Our bodies know how to break this down. We also know how to break this down. It doesn't know how to break down the trans. It's just not something that's in nature very often, so we don't have this, and so this builds up because we can't get rid of it. Okay, and that's what makes it so dangerous. Okay. Now, one of the things to note is that as you go from single, double, and triple bond, the bond distance gets shorter. That's really the big thing you need to know from this slide. Is triple bonds in general are going to have shorter bonds than single bonds. Okay, because you have the overlap is going to be, you need a lot more overlap to get this, and so they need to bring it closer. Okay. So triple bonds. So if I ask you between this carbon, a carbon-carbon double, or a single, double, or triple bond, which one's the shortest, you're going to say the carbon-carbon triple bond. Or the carbon-carbon single bonds, the longest. Now, one of the effects of this is that when you're going from a single bond, remember you only have two electrons here between these two carbons. When you put a double bond, you've essentially put 4 electrons around here. And a triple bond, you've got 6 electrons in here. And so if you notice, the red is going to be electron density. You're getting a lot of electron density in here. And so so we can use that to do reactions, okay? Because it's going to give it a partial negative character to it. And so this will be important down the road. Okay. Now again, remember from the atom, right? We've been dealing with up to this point the electrons, right? But sometimes we do have to deal with the nucleus, right? The nucleus where you've got the protons and neutrons, right? So that the protons are that's what defines the atom, right? All carbon atoms have 6 protons. That's what defines it. All sulfur atoms have 16 protons. All chlorines have 17. Okay, that's what defines the atom, right? The neutrons are there to just stabilize it, because if you just tried to put 17 positive charges together, it would blow apart, right? The neutrons are there to stabilize it. The electrons are there to perform the chemistry. Okay, but we do have to deal with isotopes. Now, the reason why I don't have to put the 6 down here to say, that it's the atomic number is because I've put the carbon, and carbon has to have 6. Has to. Okay, but it can have a slightly different number of neutrons. Okay, and so the common one for carbon is going to be 12, right? 6 protons, 6 neutrons. But there is carbon 13. And we're going to be dealing with this later, 16 and 17. And there is also a small amount of carbon 14, which is 6 and 8 neutrons, right? But it has to have 6 because it's carbon. Now this is radioactive, right? Because you sometimes hear about carbon 14 the radiocarbon dating because we know how fast it decays, and so we can tell how old something is within the last several tens of thousands of years by how much carbon 14 is left in the molecule or in the in the sample. Okay. Now the valence electrons, again, they're going to be the outermost electrons, and so to figure out how many there are, and that's how you just count over. So you go whatever the shell is, the horizontal row, and and so if you're trying to figure out how many valence electrons there are in nitrogen, you count over 1, 2, 3, 4, 5, and that's it. So in this one, it's these A numbers here, right? So 1, 2, 3, 4, 5, right? So chlorine is going to be 1, 2, 3, 4, 5, 6, 7. Okay. Now for our stuff, you don't have to worry about the d orbital stuff. That's inorganic chemistry. So if you're looking at something like germanium, you're going to go 1, 2, 3, 4. So you just kind of skip over that part, just kind of like you skipped over this part. So, but what we're trying to do is we're trying to get the everybody's trying to get their octet, well, except for hydrogen. It only needs 2. Okay, and so with ionic bonds, you're getting a complete transfer, and that's usually between a metal and a non-metal. Okay, but covalent bonds are going to be sharing. And so if you want to look at this video, it's the Dog's Teaching Chemistry one. It's very cute, stuff like that. And so the atoms want to have the same number of total valence electrons as these noble gases, and so they're going to gain and lose them or share them in order to get that configuration. Okay, so for an ionic bond, right? So lithium has, right? So it has 3 protons, right, and 3 electrons. Okay, the fluorine, right? It's got 9 protons, right, and 9 electrons, total electrons. If we move one of those over, right, lithium still has to have 3 protons, right, because that's what defines it to be lithium. But now it only has 2 electrons, right? So it's got 3 pluses, 1 minus, and so if you add it up, right, it's a positive 1. With the negatives, or with the fluorine, right, so it has to have 9 protons, right? That's what makes it a fluorine. But now it's gained one of this, and so now it's got 10 electrons, right? So now it's got 1 more electron than proton, and so it's got a negative 1 charge. So hopefully so that's why we got this, since it's a definite moving over. Okay. But with inorganic, excuse me, for nonmetals, okay, you're going to get more of an issue of sharing, okay, and how much an electron wants to be in one atom versus the other, okay, it depends on what's called the electronegativity. And this is, again, you don't have to memorize this, but know the trend is that the closer it is to fluorine on the periodic table, the more electronegative it is, okay, because remember, fluorine is one electron away from being the from being neon, okay, that noble gas configuration, and it has very few core. The only core electrons it has is those two electrons in the 1s, and so you can so the valence electrons can really feel the core protons, and so in that nucleus, okay. And so to determine if it's a covalent or polar covalent bond, okay, what we're going to be doing is we're going to be looking at the difference between these two values. So if it's formed between, so what we're going to try to do is, right, we're going to make a octet, although with hydrogen just 2. The electronegativity, so for something like this, if you have 2 the same, it's going to cancel each other out, okay. So so it's always going to be, no matter what the atoms, even if it's 2 fluorines, if you have 2 fluorines, right, the difference is 0, and so you're going to get an equal push, stuff like that. So but we are going to be switching over to these, what are called these Lewis structures, okay, and this is from Gilbert Lewis. He was a sort of titan of chemistry in the early 20th century. He realized that, okay, you know, if you try to draw it like this, where you're putting in all the valence electrons, it becomes very hairy very quickly, because you got dots flying everywhere. So for that, and so what he said is, like, look, if we put a line in here, it becomes much neater, okay, and then everybody's going to know that one line equals 2 electrons. And so I usually think about it as, if you were to do this, put a dot on either end, okay, dot on either end, and so that can remind you that there's 2 electrons in that bond, okay. And so instead of having drawn it like this, you can just put the 3 lines. Now, the lone pairs we still show, because, you know, we don't know what else to do with them and stuff like that. And so for there, you can still put dots, but for bonds, you can just deal with lines and know that it's 2 electrons, okay. Now, there is, I'm not going to go over reviewing Lewis structure. The Top Hat book does go through it. You can always go back to a general chemistry textbook, stuff like that, but we're not going to go through it here, okay. Now, do note that there are a couple of times where we can violate the octet, and this is typically, these are these third rows, those phosphorus, sulfur, and chlorine. Those are the biggies that we have to deal with, sometimes bromine. But what happens is they can start dumping electrons into the 3d orbital, and so they can violate it. But carbon, nitrogen, oxygen, fluorine, boron, they cannot. Okay, so carbon can never violate the octet rule. Okay, but do realize that you can have phosphorus pentachloride or sulfur hexafluoride. Those are totally legit molecules. Okay, and it's a little quirk of that. So, but most of the time we're not going to violate the octet rule, okay, if we don't have to. Now, one of the things we have to deal with, right, is how the atoms are formally. So this is an accounting thing called formal charge. Okay, it's just an accounting for, does it act like it has a positive charge or negative charge. Okay, and so it's electron record keeping. So remember, you're gaining or losing electrons, right? So if you have a loss of an electron, you end up with a positive charge because you have an imbalance. If you have a net gain electrons, right, you get a negative charge, right? You've added a negative charge in there. And so what the calculation would be is what the atom, where what would it normally be on the periodic table? Where did it start with? Minus where does it have now? Okay, so if it starts off with, if it wants to have 6, you know, it has 6 on the periodic table, but now it has 5. 6 minus 5, right? It's lost an electron, so it'd have a negative. It'd have a so for that, it'd have a +1 charge. right? So that because it's formally lost an electron. Now, how do we deal with bonds? Well, it turns out for every covalent bond, you split it in half, and one electron goes one way, one goes the other. Now, for forming octet, you can double count, but this is this is more of a bookkeeping thing, and we don't want to double count. So we take one electron on one side, one going the other. Now, for lone pair, it can stay with the atom that it's on, but for bonds, you have to split it in half. Okay, and so for this one, if you have ammonium. Okay, so for each one of these, we're going to remember there's an electron here. There's 2 electrons in each bond, right? And so if we're going to split it, right, it's going to look like this. So nitrogen would have 1 electron from each one of these bonds. Hydrogen would have 1 electron from its bond. And so for the nitrogen, right, if you look at the periodic table, you count over, nitrogen has 5 valence electrons. Well, where does it have now? Well, now it only has 1, 2, 3, 4. So it has 5 minus 4, so it's plus 1. Hydrogen, on the periodic table, it has 1 valence electron, right? And now it has 1 valence electron in the molecule. Okay, so it's 1 minus 1, so it's 0. And so the formal charge would be on nitrogen. Okay, and that's how you deal with all of them. So if we're looking at this one, okay, and so remember for this one, we're going to be dealing with all of these bonds have 2 electrons, right? And then we're going to be slicing them like that. And so for the oxygen, right, so the oxygen, we're going to have the 2 lone pairs that were there, and then the 2, one from this bond and one from this bond. Okay, and so it would start up, oxygen has 6 normally, okay, and then but now it has 6, and so the difference is 0. Same for that hydrogen, right? So the hydrogen has, right, one from this bond, right? And so it would be 1 minus 1 equals 0. This carbon, right? The carbon, right? It's got 1 from each one of these bonds, 1 from this bond, 1 from this bond, and so it would normally have 4. If you count over, it's 4 minus 4 equals 0. And this is a pretty boring molecule. But for this one here, okay, for this oxygen, right, it's got 3 sets of lone pairs, okay, and then an electron from this bond. And so again, oxygen, if you count over on the periodic table, it normally have 6, but now it's got 7. 1, 2, 3, 4, 5, 6, 7. So this one has a -1 charge, and so you'd put a negative there. Okay. So there you go. It's just an accounting of formally does it have a negative charge. Okay. And so if if you look at these, right, so what the atoms really want to do, so carbon really wants to have 4 bonds, nitrogen wants to have 1 electron and 3 bonds, oxygen wants to have two lone pairs and 2 bonds, right? It says a lone pair, 3 bonds, and it doesn't matter what combination it is. Okay, the halides, so fluorine, chlorine, bromine, iodine, they want to have 3 lone pairs and a bond. If it's anything other than that, you're going to have a charge to it, negative. So if you have, let's say, an extra lone pair, you're going to have a -1. If you're missing a lone pair or a bond or something like that, you're going to have a positive charge. Okay, and so this is what the atoms really want to do, and they generally want to get to this state. Okay. Now for isomers, we're going to be dealing with this a lot in later on, stuff like that. So, but for most part, so what we mean by isomers is we're looking at the relationship between two molecules. Just like if you have 2 people, you could be, your relationship could be, cousins or siblings or spouses or whatever, twins, who knows, stuff like that. So you're looking at the relationship between two molecules. Okay. For constitutional isomers, this is the loosest one. The only thing they have related is the fact that they have the same number of each type of atom. They have the same formula. Okay. In this case, dimethyl ether has 2 carbons, 6 hydrogens, and an oxygen. And if you count, you can always count them up. Ethanol does as well. This one, if you put it up next to you, you might pass out. It also smells really bad. This one, you can put it in your margarita, right? This is the alcohol that you drink, right? I mean, that's, now you will get sick if you drink this too many margaritas, but you know, just no big deal. So this also smells. This is the smell that's given off for baking bread, so you know it smells pretty good. But again, they have 2 completely different properties to it, and so they are not the same. So these are like distant cousins to each other. They just so happen to share the same formula. Okay, now we're going to get into drawing of these organic structures, and there's a couple of different ways that we're going to do this. And the primary ones, now we are going to do some Lewis structures, but primarily we're going to do either condensed structures or what are called skeletal structures. Those are also sometimes called line bond structures. I like skeletal structures because that's what I was taught, and it's kind of a fun name. But for condensed structures, what we're going to do is we're going to say, okay, so instead of having to draw out all of the bonds, we're going to make some assumptions. Okay, and so these are the core carbon, you know, the big atoms here. And if there's no, so what we're going to say is, okay, we assume that if there's not a bond shown, it's a single bond. Okay, and that the things listed after it are here. So these 3 hydrogens are bonded to that carbon. There is a single bond here. Okay, these 2 hydrogens are bonded to there. This hydrogen bonded there. These 2 hydrogens bonded on that carbon. These 2 hydrogens bonded on that carbon. These 2 hydrogens on that carbon. Now this one, because it's what's called a branch, so it's sort of going out of the plane, we do want to show that. So if we didn't, it would just sort of be floating out there. So we want to show that there's a carbon single bond here. But these 2 hydrogens, we're going to say, are on that carbon. These hydrogens are here. Now, if there's a double bond, you're probably going to want to show that. Technically, you don't have to, but it's a good habit to get into for showing the double bonds. With that. And so, if we come in here and we look at this, okay, what we're going to be interested in now, I'm going to put numbers in here just so you can, just for some reference on the carbon. So 1, 2, 3, 4, 5, 6. Okay, and so what we'll do is we'll say, okay, so we have 1, 2, 3, 4, 5, right? So 1, 2, 3, 4, 5. Okay, oops. 1, 2, 3, 4, 5, and then there's also the 6th one that's sort of what's branching off, and so you'll have number 6 here, and it'll be that carbon, and there is a bond there, right? It's coming off of it. Now, you can assume that all of these are going to be single bonds. Okay, so what are the other things attached to this carbon? Well, this carbon 1 has these 3 hydrogens, right? So it's got these 3, so CH3. This one has that group, which we'll deal with in a second, but it also has that hydrogen. Carbon 6 has these, and so we're going to put these here. So carbon 3. Okay, so that one goes here. These 2 are on carbon 3, right? And then it also has the 2 carbon-carbon bonds, which we don't have to show, so it would be like this. This carbon also has these 2 hydrogens attached, and then this carbon has these 3 hydrogens attached. And so this would be the this would be the condensed structure. Now you can get away another way that you could draw this is to actually have is to draw it like this: CH3, CH, and then put that what's branching away from it in parentheses. Okay, CH2, CH2, CH3. And what this means is all of this stuff is bonded there. Okay? And so that's what the parentheses means. And so if you want to draw something out quickly, this is usually a good way to go, particularly if you have a long chain, a long line of carbon atoms. This is an easy way of doing it as opposed to drawing it as a Lewis structure where you have to draw on each individual bond. Okay? So this, I would take either one. Both of these are completely valid. You don't have to number them. Something like that. I'm just doing this so you can sort of relate. This is this carbon. That is that carbon. That is that carbon. It's like that. So this is what it would look like. Okay. Now for skeletal structures, this is just like as the name implies, we're just looking at the inner core, the skeleton, of the molecule itself. Okay, and the way we're going to get away with this is to show, okay, we're actually not going to show any carbon atoms. Okay, we're going to assume that if there's an intersection of two lines, or I need to update this, if it's a line that goes out and does not end in a letter, okay, it just kind of goes and ends, there's a carbon actually at that end as well. Okay. The other thing we don't have to show is we don't have to show any CH bonds. Okay, so carbon, and this is important, that's why I put it in red and bold and italics and underlined, carbon atoms always have 4 bonds. They always have this. If the time when they don't is when they have a charge, so I should say neutral carbon atoms. Okay, if it has fewer bonds are shown, that doesn't mean that there's only the 2, so it has 2 bonds shown, that doesn't mean it only has 2 bonds. It means that the other 2 atoms are CH bonds. Okay, and so we fill in the rest of the bonds. You can assume that those are carbons, or excuse me, those are hydrogens coming off of there. Okay, now all the other carbons, all the other atoms other than carbon and hydrogens that are on the carbons are always shown. Okay, so hydrogen is directly attached to something else. They're always shown. So if you have an OH, you're going to draw that H. In H, you're going to again draw that H in there. Okay, but otherwise, the hydrogens that are coming off carbon, you don't have to draw. Okay, you don't draw. And so this is a calculate structure similar to Lewis structure, in that here this is what it would look like, but this is what the skeletal structure looks like. And this is where I like, especially when you're learning, is to put dots where the carbons are. And sometimes I'll do this other times when I need to sort of keep track of the carbons. Okay, and so carbon, 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 right? So the intersection. Notice how these just end, and so that we know that they're because they're not ending in a letter. That means that there's a carbon there. Okay, but this carbon here, right, has 2 bonds shown. So, but it has to have 4 bonds. So that means the other 2 have to be hydrogen. This one only has 1 shown, and so that means the bottom 2, 3, and 4 need to be CH bonds. Okay, this carbon here has all 4 bonds shown, right? 1, 2, 3, 4. So that means there's no hydrogens on there, and then this carbon here has 3 bonds shown, 1, 2, 3. So that means it must have 1 hydrogen. Same thing here, the intersection of 2 lines, or 2 or more lines, here, 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 or here, and then this line here, which does not end in a letter, there's also a carbon out there. For here again, all of these intersections are carbon atoms. Okay. Now this one ends in a letter. It ends in an O. So that means that there's not a carbon there. It's a carbon-oxygen bond going out to this, and we have to draw this. We have to draw that hydrogen because it's not on a carbon. Have to. If there's not an H there, the molecules has a lot significantly different properties to it. Okay, so you have to be careful. Okay, now sometimes you need to be able to combine a skeletal and a condensed structure, especially if you need if when we're doing the chemistry you need to deal with those CH bonds, and so so what you can sometimes do is you'll sometimes if the group hanging off is small, what can happen is you can get an inversion. So these three hydrogens are still going to be on that carbon. Normally it would be like this, right? You would say these 3 are here. The reason why we do this is to say, is to emphasize the fact that what's not happening is this. We're not going through a hydrogen into that carbon. It's a carbon-carbon bond there, and the hydrogens are kind of sticking out over there. This is not what's going on. Same thing here. This hydrogen is it's attached to that oxygen, just like this hydrogen is attached to that oxygen. But we want to emphasize that there's a carbon-oxygen bond here. So sometimes you'll see it flipped, and that's only for really small things. If you were to draw that, CH3 on this side, that's totally big deal. It's one of those things where you probably you don't have to do it that way. But if I do it accidentally, or if you see it written in a book, you'll know what's going on. If it's a larger group, then they'll just write it out like this. Now, I don't care. There's only two times that I care if you draw it as a Lewis structure or a skeletal structure. And those are going to be the questions on the first test when I say convert this molecule into a condensed structure or convert this molecule into a skeletal structure. Other than those two questions, I do not care how you draw it. You can draw a Lewis structure, you can draw a condensed structure, a skeletal structure, whatever's going to be easier for you, except for those when I specifically ask for those types of structures. And you'll see me, and you can mix and match. It's not a big deal, in any other place. Okay, so if you're drawing skeletal structures, okay, the first thing you're going to want to do is you're going to want to identify any hydrogens that are not on a carbon. So these two, because you're going to have to draw those in. Okay, all the other ones, right? You don't have to show. So let's get rid of them. Okay, and what we're going to end up doing is redrawing the carbons as dots. And so dot, 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 right? So there's a bond there, bond there, bond there, double bond there, single, double. Okay? And so carbon, 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 carbon. Now the fluorine we have to show. And now if you want to put in the lone pairs, it's a good idea to do that. But it's not required. And then this one here, right? Now you can draw this as like this with the lines in it, or you can draw it as a condensed structure. That doesn't matter with that. You can get away with either one. But that's it. That's your skeletal structure right there. So you could draw it, this one here, like you could do one when you're first, and really any time. And it doesn't matter if the double bond's above or below the line. That does not matter. You could draw it like this, very, very simplistically, or you could do it in the sawtooth form. That's fine too. Stuff like that. But while you're learning this, get it. The important thing is to get it, to draw accurately. It doesn't necessarily have to be the prettiest one out there. It's not like you're going to be publishing these things. So. Now, one of the things that has to happen, right? So we're dealing with a two-dimensional rendering of this thing, but remember the molecule's 3 dimensions, and so we have to be able to account for this. And so if you're looking at a 3-dimensional, so if you're looking at a tetrahedron, if it's in the plane of the paper, right? We're just going to have that be a normal line, okay? But if this bond here, right, is coming out at you. Notice how it's a heavy line. We call that a wedge. Okay, so that means that this CH bond is coming out at you. While this bond here, which is going away, we indicate that with a dash. This will be more important when we get to chapter 5. But if you see it, that's what it means. Okay? And so, like this hydrogen and that hydrogen, right? They're coming out at you. While these two hydrogens are going away. So in here, this OH is pointing out at you, the hydrogen is going away. Here, the 2 bromines are going away, these 2 hydrogens are coming out at you. And then this one, the bromine and this carbon-carbon triple bond here, these are in the plane of the board. This hydrogen's coming out at you, the OH is going away. Okay? So that's how you read these things. Now, next up is going to be resonance structures. And so this is one of those things that happens where it's a way of dealing with an inconsistency that arises with Lewis structures and these sorts of structures, is that they aren't really what's happening, but it's easier for us to visualize. Okay, and so if you look at something like acetate, And we know from other molecules that the bond length between a C double bond O is typically 120 picometers, but a CO single bond is 135. When you look at the bonds here in acetate, if you can measure this bond length here and that bond length there, they're both 127. All right, this should be 135 and this should be 120, but they're both 127. And the reason for that is that this structure here is just as valid as this structure here. And in fact, what's going on in nature is that it's actually this molecule here, right? There's a 1.5 bond for each of them, which is why it's halfway in between these molecules. And so this is actually the reality of it, if you were to take a snapshot of the molecule, but we can't sort of comprehend a half a bond, right? So there's a 1.5 bond here, and there's 1.5 bond there, but it's hard for us to visualize that. And so we have to go through this process of sort of explaining what's going on, okay? And this occurs when there are several valid Lewis structures that can be drawn simultaneously. And so for here, what you can do is you can have the double bond between these, this carbon and oxygen bond, or this carbon and oxygen bond. There's no reason why you can't have these help out or these help out. And so it's actually going to be a mixture of the two. It's going to be the average of these two, okay? The other thing is, it's this, the individual resonance structures. Okay, it's sort of, they are imaginary. It's only just the resonance hybrid that's sort of this weighted average of each of these resonance structures is the only real true structures. But we can't. It's hard for us to think about a half a bond or a third of a bond or something like that. Okay, and so what we do is we sort of, sort of things that are more common. Things like that. So the idea is, I thought this was a great picture. So let's say you're trying to describe a duck-billed platypus. Okay, sometimes it's easier to think of it as a type of duck, right? It's got the bill, it lays eggs, it's in the water all the time, whatnot. Okay, sometimes it just seems more like a duck. Other times it's better to describe the duck-billed platypus. Its behavior is more like an otter. Okay, it's it's small, it's long, it's furry, it lives on things like that, and it's a mammal. Okay, but these are approximations for what the real world, for this weird animal here. These are more, we are more familiar with a duck and an otter than we are a duck-billed platypus. So sometimes we can use these as proxies, but we have to keep in our head that this is really what we're describing. So this would be one Lewis structure, this is the other Lewis structure, this is the hybrid, because this is what's actually going on. Okay, and so it looks like all the different resonance structures are not equally important. Okay, and so what's going to happen is some are more stable than the other, and so the more stable, okay, it's going to have the greatest number of atoms with their Philid octet. Okay, most covalent bonds, and the fewest number of atoms with formal charges. And particularly if those charges, if you have a plus and minus, you don't want them far away from each other, right? You want them together with that. And so the charge separation is also an issue. And so if you look at these two structures, you say which is the more stable. Now we don't have to worry about the carbon-hydrogen bonds, right? So with that, but if you look at, you ignore those, right? So with that, so you've got 1, 2, this one has 3 bonds, 3 covalent bonds. This one has 4. 1, 2, 3, 4. Okay. This one, this carbon here, its octet isn't filled, right? Because it only has 3 bonds, right? 1, 2, 3. So it only has 2, 4, 6. Here, it has 1, 2, 3, 4. Oh, it's because of 4 bonds. This oxygen here also has its octet filled. Yeah, it's charged, but it's 1, 2, 3, 2, 4, 6, and then the 8 from the lone pair. So this one is the more stable of the two. Even though oxygen has the positive charge, this is more stable because everybody's got their octet, we have the most bonds, and everybody's generally happy. Okay, the reason why this happens is because it provides stability overall to the molecule. Okay, the electrons are delocalized, and that it allows, if there's a charge, it allows atoms to this burden of the charge. Okay, and so I always describe it as if you're trying to move a couch. You moving a couch, if you're having all the burden of that couch, it's going to be a royal pain in the butt. But if you can have a friend help out or multiple friends help out, it's going to be a lot easier, right? So now you and a friend are moving a couch. You're both bearing that weight, right? You're both bearing, in this case, it's very similar to bearing that charge. You're having two electrons bearing that charge, right? It's going to be a lot easier on the molecule, okay? And stuff like that, and that's it. And so that's why it likes to do it. And especially if the different resonance structures all have the same stability, that's even better, right? So this is benzene, and so if you look, it's the electrons have just moved over, and so there's no difference between these two, and so benzene is incredibly stable. Okay? And it's not just the molecule rotated. It's easier to think about, like, if one of these was not a carbon, or if you put an isotope some there, and you can, for reference, okay, it's not just things moving, okay? All things being equal, the more resonance structures you can draw for a molecule, the more stable it is. Okay? But the biggie with this one is that the atoms cannot move. Only electrons can, okay? And so for here, if we want to look at electrons, so we're going to move these electrons over here to make a double bond. And so this time, if you calculate the formal charge, this one will have a plus charge. For this one, because it only has 3 bonds, this carbon has a plus charge. It's not necessarily the charge moving, it's the electrons moving, and now you go back and you calculate the charge, now it's this carbon. For this one, this is not a resonance structure, because if you notice, what's happening is this hydrogen here is moving over to that carbon, right? It suddenly goes from 1 carbon to 2, or one hydrogen to 2 hydrogens. Well, you can't do that. That's an actual reaction, okay? And so when we're describing these things, we have to know about the different types of arrows, okay? And so if you have a single-headed arrow, okay, you've seen these, right, since the beginning of chemistry, that means a reaction has occurred. If you have two either single-headed or double-headed arrows, that means that there are, but you have to have 2 of them, that means there's an equilibrium. It's reaction going forward, reaction going back. If you want to describe resonance structures going between 2 resonance structures, now you have a double-headed arrow. It's not this, it's a single line with 2 arrows on either side. And you can see that here, right? Between these 2, there's that double-headed arrow. That means we're flipping between 2 possible resonance structures. Okay? Now for this one, if you have a curved arrow, what that means is it's describing how electrons are traveling. And you can have a single barbed arrow, like this, okay, and it has its own little point on it, or a double-headed, or a double barbed arrow. This means that you have you're talking about 2 electrons moving, and this one you have 1 electron moving. Okay, and so it's going to be where the electrons are going or where they're going to. So it's no different than a GPS arrow, right? Where those electrons start, where are they going? So they're starting here and they're going over there. Okay, these electrons are starting here and they're moving over there towards the positive charge. Okay, over there, and they're moving to between these 2 carbon bonds, between these 2 carbons. Okay. Now, okay, so for something like this, okay, the first thing to do is to start the charge. Now, the one that I give you is more organic. It's not going to have all of these charges, but we got to look at one. So you start at a charge and you say, okay, let's start here at this oxygen here. And so what does oxygen really want? It wants 2 bonds, 2 electrons. So what we can do is we can say, okay, hey, how about if instead we take one of these electrons and we can make a new bond, right? We can make it there. But the problem is this nitrogen already has its 4 bonds, and so it can't have a 5th bond. And so you can't like push these electrons away, because that would cause this oxygen to break apart, or this oxygen to fall off. But what we can do is instead we can move these up there. Okay, and so if we're going to draw the resonance structure, what's going to happen is you would have this. Right? And so this set of lone pairs became this second bond here. This second bond here became this 3rd set of lone pairs. Okay. Now we could have just as easily said, okay, well, hey, let's start with this oxygen and move that down. Again, we're going to have that same problem with the nitrogen having a fifth bond. It's got to get rid of one, and so let's go there. And so, again, these electrons are going to come up here for a third set of lone pairs, nitrogen. We haven't done anything to this oxygen in the blue structure, so it just stays put. Oh, sorry. Forgot to put the positive charge there. Okay, and so now this is another completely valid resonance structure. And so what we've done is said, okay, the negative charges are here. Are they over? Are they in the bottoms, or are they to the lefts? Now we could just as easily said, okay, well, what's wrong with the nitrogen here? Well, okay. Oops. What if instead this nitrogen, right, it wants to have 3 bonds and lone pairs. What if it says, okay, I'm going to take those lone pairs all by myself? And so what you would end up with is this. And so now those electrons instead, if we would have started with the black structure and moved these electrons up here, we would have gone here. Now this isn't a particularly great Lewis structure, or resonance structure, because you've moved the positive charge way out here, right? But it's still really valid. But these three here are going to be the most stable, and so it's going to be an average of these 3. Okay. This one isn't particularly stable, so it's not going to show up very often. All right. So there you go. Now for polar covalent bonds, okay. So with that, and so what we're going to be talking about, right, is that the electronegativity difference between the two. Okay, and so fluorine is more electronegative than hydrogen, so the electrons are going to spend more time over here. So with that, and so the molecule itself is going to have a partial negative and a partial positive. Carbon and hydrogen, there's not really that. We usually consider that to be a covalent bond. And notice how there's not really much difference, there's no charge distribution, really, in something like this. But for here, oxygen's way more electronegative than carbon is, so the electrons are going to be spending more time out here on the edge. Now, it doesn't matter that it's a double or a single or a triple bond. We're just looking at the difference between the atoms. And for this one here, borohydride, right, hydrogen's more electronegative than boron is, and so the electrons are going to be spending more time out here. Okay? And so we can indicate that with an arrow. Okay, and so you can either, I'm sorry, I should have proven this. If you want to indicate a partial positive, so the electrons are spending more time, say over here, you can put this delta minus or delta plus. Okay, so it's a lowercase delta or plus or delta minus. That would indicate which side it's on. The other way you could do it is with this arrow. Okay, and so it's a double. You don't see this very often. It's pretty much just for this part. Usually we use the little deltas, but it's totally fine. The arrow points towards the negative side, and then the other side is going to have a crosshatch. And I always thought that looked like a positive. So this is always going to be on the positive side, and this is going to be the negative. And so what you can do is each atom, each bond or whatever it is going to have their own little arrow. Okay, so here it's this way and that. Okay, and the reason for that is we're going to talk about is dipole. Okay, and so that's indicated by a microsign. Okay, and what we're going to be doing is we're going to look at those arrows and just add them up. Okay, and so if we look at something like this, right, notice how these in CO2, it's the classic one that doesn't have a dipole. Notice how these arrows are equal and opposite. So that means they cancel each other out. Like if you had a big burly guy on this side in a tug of war, a big burly guy on this side, right? Tug of war, nothing's going to change. But for here, you only have it pulling one way, right? Big burly guy on this side, but on this side you've got a 5-year-old, right? It's going to, it's going to go that way. But remember so what's going to happen is there a partial charge on one side of the molecule? And so, but remember, dipole moment and polar character are actually two different things. So methyl chloride here is a pretty big polarity, but it's not particularly polar. Okay, there's a lot more complicated than that. And so for methanol, it's infinitely soluble, even though it's less polar character. And all of this is going to be driven by electronegativity. Lone pairs also give it partial negative charge to the molecule, right? Because they're electrons, right? They're negatively charged. And so if you have something like H2, Cl2, right? There's no dipole because there's no electronegativity between the two. But if you have some of these, if they're symmetrical, so CH4, right? They're going to cancel each other out. But these guys do not. Okay, and so if you have something like carbon tetrachloride, right, you're going to have CCl, right? You're going to have your arrows like this, right? These two horizontal ones are going to cancel each other out. These two vertical ones are going to cancel out. So this one has a dipole of 0. But if instead we looked at chloroform, which has one of those chlorines changed to a hydrogen, now these two are going to cancel out, but this one here, there's nothing to cancel it out, right? Because this is a covalent bond, and so these two cancel each other out, but this one doesn't have one, and so this molecule here has a dipole to it, and you can see it here, 1.2. Okay, and so cis and trans isomers also can have a dipole if it's a cis, right? So they're both going to be pointing down, and to determine the dipole, what you're doing is you're going halfway in between the arrows, and so you're sort of averaging them together. So this one, so this would be the overall dipole here. Oh, so I should have said, okay, so what you're looking at for here is these two cancel each other out, but you've got this one that doesn't. And so the overall dipole would be like this. Overall dipole like that. Okay, these two cancel each other out, so you don't have to worry about this, but the overall dipole of the molecule goes like this. So for cis, right, these are both pointed down, so the overall is going to be halfway in between, so the overall is going to be here. Here, they're equal and opposite, so they cancel each other out. So this one has no dipole. Okay? And so this allows for different interactions. Okay? Because if you're looking at melting point and boiling point, what you're talking about is intermolecular forces. Okay? And so for solid, you've got a lot of forces, and typically, if you have a lot of interactions between them, you're going to have higher boiling and melting points. Okay, so for ionic bonds, right, you have a positive and negative. This is going to be an incredibly strong interaction, right, because it has a full positive, full negative. Okay, but for nonpolar or for polar covalent bonds, you can have this dipole-dipole interaction. So if you've got these dipoles here, they're going to align, and so the partial positive, partial negative, partial positive, negative, positive, negative, right? These are all going to line up. Okay, and so this it's not an ionic bond because it's not a full positive and a full negative, but it's going to be fairly strong. Okay, and the larger the dipole, the stronger the dipole interactions. And then you can also have a very special case of this dipole if you're dealing with a hydrogen atom. If it's a hydrogen that's not on a carbon, you're going to have a pretty big difference in the amount of electronegativity difference. And so you're going to have a big partial positive and a partial negative here. And so this hydrogen is going to seek out the lone pairs on another molecule. And so that bond there is quite strong. It's stronger than a normal dipole bond. It's not as strong as an ionic bond, but it's much stronger than a normal dipole-dipole bond. And so you've got a hydrogen bond donor, which means it has a hydrogen that it can give to make the hydrogen bond. And then the acceptor is the one that has the lone pairs. It's going to accept that hydrogen to make this polar covalent bond with. Okay, and so water is particularly one of the reasons why it's so strong is because it has two hydrogen bond donors and two hydrogen bond acceptors, because it's got the donors because it has two OH bonds, and it's got two sets of lone pairs which act as acceptors, and so you've got this huge network of hydrogen bonds. And these are extremely important, not only dealing with water, but other biological systems, because it's hydrogen bonds that holds these, the base pairs of DNA and RNA together. Okay, it's this interaction between these two. But then also with protein secondary structures, so in the backbones, if you're looking at regions, so you look at these alpha helices and beta sheets, what's happening is what's holding those together is the hydrogen bonding between the backbones. It's like that. So this hydrogen bond between the C double bond O, which has the lone pair, and the NH bond, which has a hydrogen on a nitrogen. Right? You're going to have a hydrogen bond there. Okay, and so the more hydrogen donors and acceptors, typically is going to be the higher melting and boiling point. So if you're looking at hydrogen bonding melting point, you just add them up. And so if you're looking at it, let's do donors first. So donors, right? How many hydrogens are on? How many hydrogens are not on a carbon? 1, 2, 3, 4. On this one, we only have 2. So, and then for acceptors, right? So how many sets of lone pairs do we have? Well, 1, 2. So this has 2. This one also has 2 sets of lone pairs, and so this would be 6, and this would be 2, so 4. And so this has more of everything, and so this would be the higher boiling. This would be the higher boiling. Okay, so the other thing that happens is if you don't have any dipole moments and you don't have these ionic bonds, how do things even come together? And so this was described first by Fritz London, and you'll hear this of the London dispersion forces. And so he was a Duke chemistry professor from my alma mater, and so he would have probably won a Nobel Prize, but he got into a car accident and was killed before he was awarded one, and you can't award one posthumously. So that what he said is that you can get these instantaneous dipole moments, okay? And so, and this is what's going to be important in hydrocarbons, is that if you've got one of these, if you got, in this case, propane, you know, normally they're all polar covalent, but if something happens and the electrons just so happen to move up here, what's going to happen is these electrons here are going to repulse the electrons here, which pushes them up here. And so now you've got, you know, positive, negative, positive, negative, positive, negative, and that induces all of these. And it's an instantaneous thing. And so you have some interactions for here because you can get these sort of just statistical quirks of, oh, hey, the electrons just so happen to be a lot of them on this end of the molecule. That creates a very slight charge distribution, and that causes the next one to the electrons in the next molecule to repulse a little bit, and so now it gets a partial positive, and so you can get these interactions. Okay, and so this is going to be significant in nonpolar molecules. So if you're talking about oils and greases and other sort of hydrocarbons, this is the dominant one. Okay, and so the strength of it depends on what's called the polarity, the polarizability, and it's really how easily can this thing be distorted. And usually, what happens is the more polarizable, the higher the boiling, right? Because there's more interactions, and increases with the number of electrons in the molecules, the bonds, lone pairs, or whatever. Okay, but also how compact it is. Okay, and so the more stretched out something is, right, the higher the boiling point, okay, which is why the things that are compact have a higher boiling point, okay, and so this is the and so here it's more stretched out, okay, and so I'm sorry, I may have said this incorrectly. It's the more something is stretched out, it's the higher the boiling, stuff like that. And so, which is why this may be a solid and this may be a liquid. Okay. Other terms to know are hydrophilic and hydrophobic. Okay, hydrophilic just means that it dissolves in water. Hydrophobic means that it dissolves in, it doesn't like water. And so if hydrophilic means it water loving and water fearing. Okay, and so large oils are hydrophobic. Small alcohols they dissolve easily in water. Okay? So why is that? Why is it? We always talk about like dissolves ice, but why is that? Why does that happen? Well, it turns out what you're doing is what is the dominant interaction between two molecules, and does it get interrupted? Okay, and so if you have pure hexane and pure water, right? When you put in the hexane, right, you're messing up the hydrogen bonding of the water, right? So the strongest interaction for water is hydrogen bonding. For hexanes, it's just London dispersion forces. So it disrupts that. But if you're looking for an alcohol and water, right, they can both hydrogen bond, and so you're not disrupting the hydrogen bonding network, and so that's why you get that's why they dissolve, because you're not interrupting this. And so you look at the strongest force and do the things both have that. If they do, then they'll dissolve. But if you have a hydrogen bonding and the dominant force is these induced dipole, these London dispersion forces, then you're going to have a problem. Okay. And so if you're looking at this, which is going to be most soluble in water, right? So remember, water is HOH, right? So this is going to be hydrogen bonding. That's the strongest interaction between this. For this one, it's this induced dipole. That's because it can't do any sort of hydrogen bonding, and it doesn't have a dipole moment, or it doesn't have dipole interactions or anything else like that. This one, it can at least do. It's either going to be dipole or it's an H bond acceptor, because it's got lone pairs in it, so maybe a little soluble. But this one, because it has the OH, it can do hydrogen bonding, both acceptor and donor, and stuff like that. And so this one is going to be the most soluble in water. Okay. And so generally, the rule of thumb is, as you increase the dipole to solvent, the more likely it is to dissolve a salt. Okay, because ion dipole. And so it's weaker, stuff like that, but stronger with dipole-dipole interactions. Okay. Now, what happens is, if you're trying to dissolve something, okay, what happens is the charges actually the molecules get pulled apart, and you have solvent going all the way around both of them, and so you get this solvent shell. The ion is solvated. Okay, so you don't. There's going to be a distance between these two, and it's going to be covered in say water molecules or whatever. Okay, but hydrogen-carbon length does affect solubility. Okay, because what happens is, as you get more carbon on here, the induced dipoles, so the London dispersion forces, those are going to be more increasingly important. Okay, and so, and you can see this, as you add carbon, it becomes less and less likely. Okay, and it crosses over. If you look at the number of carbons versus hydrophilic groups, if it's 3 or 1 or less, then it's probably going to be soluble in water. But if it's higher than that, then probably not. And so if you look at this one, you have one, for this one, each one of these you have 1, but this one you have 2. Okay? And then for this one, right, you have 1, 2, 3 carbons. Okay? This one you have 1, 2, 3, 4, 5, 6 carbons. And this one you have 1, 2, 3, 4, 5 carbons. So the carbon to the carbon ratio here is, in this one it's 3 to 1, 3 carbons, 1 hydrophilic group, 6 to 1, 6 carbons, 1 hydrophilic group, and this one is 5 to 2, or if you want to simplify it, 2.5 to 1. Okay, and so both of these are going to be soluble in water, but this one is not. So, because this is less than 3 to 1. Now, the other thing would be what are called protic and aprotic solvents. Okay, this is going to be important as we move along for reactions. Okay, so because some work better in protic, some with aprotic. Protic means it has basically it has a hydrogen that's not on a carbon. It only has to have 1. It can have 1 or more. It can have 5. Who knows? Doesn't matter. But if it has at least 1 hydrogen that's not on a carbon, it's considered a protic solvent. If all the hydrogens are on a carbon, it's aprotic. Okay, so water is the classic protic solvent because it has hydrogens on there, but also ethanol, right? So here it is. Yeah, it's got hydrogens that are on carbons, but it has at least one that's not. Acetic acid, so vinegar is another one. Okay? It's right there. But for here, DMSO, dimethyl sulfoxide, acetone, DMF, all of these have, all of their hydrogens are connected to carbons. Okay, here, all of them. So these would be considered aprotic solvents. Okay. Now the thing about aprotic solvents is they do have some difficulty solvating ions, and the reason for that is they can point there, so it's pretty good at doing positively charged things, so because it can get the negative right in here, right next to it. But for negatively charged ions, right, it's hard because it's the partial positive is up here in the sulfur, okay, and you've got a bunch of these are called methyl groups. These groups here kind of get in the way, and so it has a difficult time solvating chlorine, and so you can have these issues of aprotic solvents generally don't dissolve polar things very well, or salts very well, I should say. And it's because of this sort of steric issue. Okay? Last thing is dealing with soaps. Okay, and so soaps, these are one of those with the detergent industry, right? This has been around for thousands of years. They've kind of stumbled upon this, and it turns out that what you do for this, and the classic one is SDS, sodium dimethyl sulfate. You see this in the lab, you see this in shampoos and whatever. Dawn detergent. Okay, what you get is a long carbon chain with a very highly polar group on it. Okay, and it can be a sulfate or a carboxylate, things like that. What can happen is, and it doesn't have to be negative. You can actually have some that are just have a lot of polar groups on there. What can happen is when you put this into water, it self-assembles, okay, into a capsule, and so these polar head groups, these are called head groups, they all want to be with the water, right? Because they're negatively charged. They want to be with the water, okay? But the greasy part in the middle does not. But that it wants to be with all the other greasy parts. It wants to hide from the water, right? Because it doesn't want to disrupt it. And so it self-assembles like this. And so when you have a greasy stain on your shirt, okay, what's going to happen is when you put it in the washing machine, this sort of capsule is going to bump into that, and the greasy stain doesn't want to be in the water any more than anything else greasy, but it sees the inside of this capsule and says, ooh, there's a greasy spot there, and so it hops in there, and so now it's floating in this capsule. This greasy stuff is floating in this capsule, and when the water gets washed away, it travels with it. That's why you have to rinse off your car when you're washing it, right? If you just let it dry with all the soap on there, it's still, all the stuff's still there. You got to wash it away because you're taking all the water molecules that have the grease with it. Okay, and so you're going to have this greasy core. You're going to have this hydrophilic, right? So with that water part on the outside, and so it can take things with it. And so it's a pretty slick molecule. And so if you had some dirt or whatever it is, you've got this water, you've got the solvation, you've got all of these head groups on the outside, some of that, and then you can put grease in the inside, greasy stains in the inside. So, okay. So that was a long one. So with that, so good luck.